Welcome to Operating Systems lecture 27. Right, so far we have looked at locks, condition variables, semaphores. We also looked at lock-free methods like transactions, and one manifestation of that called compare and swap. Right. So these compare and swap instructions are also what are called lock-free methods of dealing with synchronization, and there are advantages of doing lock-free synchronization as we are going to discuss later in this course. Right. So today I am going to discuss these in the context of XV6, and let's look at how an operating system like XV6 is using synchronization under it within itself. And so XV6 uses locks. XV6 uses condition variables, but in a different form. So instead of calling them condition variables, he calls them sleep, wake up. All right. So the semantics are similar. Sleep is conditional wait, and wake up is notify. So instead of calling them condition variables and wait and notify, he calls them sleep and wake up, and we are going to see what are the subtle differences between sleep and wake up and wait and notify, and doesn't use semaphores. So that's fine. Semaphores are anyway higher level. You can always simulate anything that you need with semaphores using locks and condition variables. All right. So let's look at how the acquire function is implemented in so let's look at XV6 locks. Right. So let's look at how XV6 is implementing locks. So this is sheet 14 on your listing. Okay. That's the lock function. That's the acquire function basically. Let's see what the lock structure is before that. So lock structure, if you want to initialize a lock, you basically have three fields in the lock. One is the name. Name is just for debugging purposes if you want to know what lock it is. So it's just for debugging purposes. You don't really need it, but they're using it for debugging. Then there's this locked variable that we know about. That's the state of the lock. And then also which CPU is holding it. That's also again only for debugging. You don't really need it strictly, but that's it helps in understanding what's going on. All right. So this is the acquire function. It disables interrupts. So push cli is going to disable the interrupts on the current processor. So notice that the acquire function disables interrupts, uses this loop to atomically set the locked variable to 1, sets the CPU to the current CPU value, and this is some debugging function which allows you to log exactly who called this lock, and that's it. So what does it mean? When you get out of acquire, the interrupts are still disabled, right? Because you called push cli and you never called pop, right? You never re-enabled interrupts. So for the entire critical section in this spin lock, the interrupts are disabled. So why does XV6 need to disable interrupts in the entire critical section? So one answer is that if there's a timer interrupt within the critical section, then it can get swapped out and somebody else can get to run, and atomicity can get violated. Is that right? No, because the other thread should also be taking the lock, and it will not get the lock because it has already called the exchange instruction here, right? So it has set the lock variable to 1. So any other thread will not be able to be able to acquire the lock.
So because if there is an interrupt handler, then basically so it may try to reacquire a lock which was acquired initially by the kernel.
Right. So what if the interrupt handler also tries to access shared data, right? So we are within the kernel, and it's possible that whatever data you are accessing, the interrupt handler also tries to access the same data. All right. So it's not about multiple threads. Recall that we have been talking about mutual exclusion across threads. Mutual exclusion across threads is easily handled by this atomic exchange instruction, right, on multiple CPUs. But what about mutual exclusion between a thread and the interrupt handler, right? If an interrupt gets to run in the middle of a critical section, then and the interrupt handler could touch the data that you have in the middle of your critical section, then we need a way to protect it, right? So what are some ways to protect it? You could say, oh, won't the interrupt handler also try to acquire the lock, right? But if the interrupt handler tries to acquire the lock, then you have a deadlock right there, right? So you got an interrupt, the interrupt handler gets to run, and the interrupt handler tries to acquire the lock that's already held. right. So that's not a good thing, and interrupt handler will likely run with interrupts disabled, so that's not a good thing. So you basically have a deadlock. So basically, to protect a thread from the interrupt handler, from concurrent accesses by the interrupt handler, you disable the interrupts for the entire critical section. The reason this is acceptable in XV6 is because you will expect that the critical sections are small, and critical sections that are protected using the spin lock are small, and those critical sections are indeed need to be protected against accesses from interrupts, and we're going to see some examples. Right. In general, when you write your programs, you won't worry about, so let's say you have your own program, or you write your own kernel thread, and that thread has nothing to do with an interrupt handler. Then you won't use XV6's spin lock. You would probably want to use your own spin lock that doesn't disable interrupts, right? Because you don't care about atomicity with respect to the interrupt handler. Okay. So the interrupts are disabled for the entire length of the critical section. Acquire leaves the interrupts disabled. Why do I need push CLI? Why can't I just use CLI? Just to ensure that if there are nested calls to acquire, if they're nested locks, so you acquired lock 1 and then you acquired lock 2, then you have a count of how many times CLI was called, right? And so that many times you have to call STI before you actually re-enable the interrupts. So if you have nested locks, then that's why so push CLI is nothing but it just increments a counter. It's a per CPU counter that it increments, basically saying how many times CLI has been called. Okay. All right. So that's acquire, and let's look at the other things. So notice that this holding function, what is it doing? It's just checking that whether I'm holding the lock already, whether this CPU is holding the lock already. So this is just a debugging thing really, and the reason this is you can check this is because you also have a field called CPU, right? So holding is just going to check that if the same CPU tried to acquire the same lock twice, that's a bug, and you want to just tell the programmer right away that there's a bug in your program, right? Rather than him have to find it in a roundabout way. So this is just a debugging aid. Right. In general, if you didn't have the CPU field, you won't have been able to make this check, and that program, if you have written your code correctly, that's still correct, but it's a debugging aid for you. Right. So I mean the other semantics in this sort of this slightly subtle semantics are that a lock is actually held by a CPU, right? So I mean that falls out from the fact that you disable interrupts. So a thread and a CPU basically mean the same thing, because you've disabled the interrupts. So if you disable the interrupts, the thread is now stuck to that CPU, right? It cannot now move anywhere. So now the lock is not really you can say that the lock is actually for the CPU and not for the thread. On the other hand, if you didn't disable the interrupts, the lock should have been per thread, because if the thread gets switched out and goes to another CPU, then that thread is holding the lock, not the CPU that's holding the lock, right? But because you have disabled the interrupts, now the thread is stuck to that CPU, so you can call it a per CPU lock instead of calling it a per thread lock, right? But yeah, so both of these are sort of interrelated. But I guess the point is that if you didn't care about atomicity with respect to the interrupt handler, you didn't have to do push CLI. All right, okay. So that's acquire. Right. So let's look at the other things. So of course, this loop we are very much familiar with. Just trying to atomically set it to 1, and if it doesn't find it to be 0, it just keeps spinning. Right. That's a spin loop. We know this. And then it just says, just sets the CPU variable to that I'm holding this lock basically. Is it okay to put lk.cpu above while loop? Firstly, until and unless you have acquired it, you should not. Secondly, there can be racing accesses to CPU, right? Because this while loop is protecting, so you can be sure that only one thread or one CPU is within this region. But if you put this above it, then there's a race condition on the CPU field of the lock. Right, so because you put it after while, you can be sure that there is no race here. Okay, and then let's look at release. So this is the release function, and once again there's this debugging aid which says if not holding lock, then you panic that you're trying to release a lock that you're not holding. That's fine, and you set CPU to 0, and then you exchange locked with 0. So once again, why do I need an exchange? So I could have just said lk.logged is equal to 0, but instead the programmer chooses to use the exchange instruction to do this. Why? Because so that there is a fence, there is a barrier between so that neither the hardware nor the compiler is able to reorder these instructions in any way. All right. So that these instructions are serialized, with respect to each other. In other words, exchange instruction acts as an implicit fence or barrier, right? So the exchange instruction acts as a barrier, so these instructions cannot get reordered with the other instructions because of the exchange instruction. If you had just written lk.logged is equal to 0, the hardware was free at runtime to just reorder these instructions, right, as we have discussed before. Alright. Now is it okay to put lk.cpu after exchange lk.logged? I mean, is it okay to swap these two instructions, these two statements, 1508 and 1519? No, because there will be race conditions on this statement, right? As soon as you release the lock, other people can now, access the CPU variable, because another thread could have taken the lock and now it may be trying to write to the lock, and here you are trying to write to the lock, so there are two concurrent accesses to the CPU variable, and so now there are two concurrent access to the CPU variable. So you know, quite obviously and smartly, the programmer is just using the same locked field to also protect the internal structures of the lock, internal fields of the lock variable itself. Apart from the critical section, the fields itself are being protected by this locked field. All right. Okay. Now let's look at sleep and wake up. All right. XV6, sleep and wake up. This is just, you can call it wait and notify. Now these are just this is just an incarnation of a condition variable, and let's see how they are used. So sleep. So the implementations are on sheet 25 of sleep and wake up, sheet 25 and 26, and let's see what's the idea behind sleep and wake up. So you have a function called sleep. Let's look at the signatures of the functions. So there's a function called sleep that takes an argument void star channel. Let's discuss what the channel is, and struct lock star mutex, right? And then there's wake up, and wake up just says void star channel. All right. So this is very similar to you know, wait, except that instead of a condition variable, I am using this pointer called void star channel, right? Instead of saying struct CV star CV, I am saying void star channel, and similarly here I am saying void star channel, right? Apart from it, the semantics are exactly identical. Sleep is going to start waiting on the channel and release the lock, release the mutex atomically, and wake up is going to wake up all the threads that are waiting on the channel, right? So identical semantics. Now question is, how can I just say void star channel? Why don't I need a struct CV here? Recall that unlike locks and semaphores, the condition variables are a stateless abstraction. You don't need any state inside the condition variable. You don't have any field called logged or anything of that sort, or a counter or anything. So it's a completely stateless abstraction. So you don't even actually need to have a variable specifically. All you need to say is that there is some number that I'm going to sleep on. Right, that number in our condition variable examples was the address of that condition variable. Instead of that address, instead of actually wasting memory or using memory to declare that condition variable, you could just say I'm going to sleep on some channel, some number. That number may be tied to the logic of your program. You don't need to. So earlier I was declaring a condition variable for the logic. So for example, I had not full and not empty. I'm saying I don't need to declare these variables because these variables don't have any state anyways, so why am I wasting some memory maybe? So instead of doing that, let's just use some channel which is just a number, right? So condition variable was also just being used as a number, as an address, so why don't we just use it as an address? Okay. All right. This is fine. Okay, so let's see, I mean at a high level, what does sleep do? Sleep is going to, so it takes two arguments and just going to say, let's say whichever process calls sleep is going to say curproc dot channel is equal to channel, and curproc dot state is equal to sleeping, and it's going to release the lock, right, and then it will call the scheduler so that somebody else can get to run now. So it has made its own state as sleeping, and now when it runs the scheduler is not going to schedule this process because this process's state has become sleeping, right. So I am just trying to develop the implementation of sleep, how it would be implemented under the covers. We have discussed the semantics of condition variables already. All right, now let us look at wake up, and this whole process has to be atomic, right. What does atomic mean? No other process should be able to inspect kerproc while I am doing all this, right. For example, if somebody calls wake up, then he shouldn't be able to inspect kerproc while I was sort of in the middle of doing sleep, right. So how I am going to make it atomic, let us defer that discussion, but let us just say this is atomic, right. And then let us see how wake up is implemented. Well, wake up is just this, it will just for each p in the proc table, right. So I have a global list of all the PCBs or processes. If p dot channel is equal to channel, right, and p dot state is equal to sleeping, then do what? P dot state is equal to runnable, right. Okay, so don't we change p arrow channel? It doesn't matter. I mean, channel is only valid if the state was sleeping. If the state is runnable, then there is no, I mean, channel is meaningless. Do I set all the processes to be runnable or only one? All, right. That's the semantics of wake up or notify, that all the processes are going to wake up. That's the semantics that we have discussed. There are different semantics in literature, but the semantics that we are working with are that wake up is going to wake up all the threads. All right. Okay, once again this whole thing needs to be atomic. What does it mean for this whole thing to need to be atomic? While I am doing this check, no other process should be able to read or write the struct proc structure, right. This proc table should be sort of exclusive to me, right. Or for example, this one is also touching kerproc is also part of the proc table, right. So kerproc is just a pointer inside your proc table. So even this should be atomic with respect to that, right. So in other words, it shouldn't happen that in the middle of while I am in the middle of this code gets to run, right. So sleep and wake up need to be atomic with respect to each other. How do you ensure atomicity? By a lock, right. So what do you think is the easiest option here? Just have a lock for the entire p table, right. Good enough. So just have a lock for the entire p table, have acquire p table here and release p table somewhere here, right. Okay. So let us say acquire p table, release p table, acquire p table. When I say acquire p table, I am really saying acquire p table dot lock, right, and then release p table. Okay, so it makes it sort of atomic. Is this correct? Is there a problem of deadlocks? Can there be a problem of deadlocks? Sure. Firstly, if the lock that we are trying to acquire is a p table lock, then the same thread. So if this argument is also equal to p table lock, then there is a problem. So firstly, I need to handle this special case because I am inside the kernel. It's possible that somebody wants to sleep, and the mutex that's protecting that critical section is actually the p table lock itself. So I could just say if lock is not equal to p table lock, then acquire p table lock, right. Let me write it clearly. If lock is not equal to p table dot lock, acquire p table dot lock, right. Similarly, when I release the lock here, I don't need to do two releases, I just need to do one release if lock was equal to p table dot lock. Is this okay? Is this am I safe now? Interrupt handlers also acquire p table lock. Is that a problem? No, because we know the acquire function will disable interrupt completely. So if I am within this region, I can be sure that interrupts are disabled. So no interrupt handler will get to run. So that's the whole idea why we had push cli inside acquire, right? Don't we need to worry about one more thing to ensure that there are no deadlocks? Order of acquisition of locks. Don't we see that there are two locks here? One is the lock that's already held before we call sleep, and another is p table dot lock. So there are two locks that are going to be acquired, assuming lock was not equal to p table lock. So the caller acquired p table lock, then he called sleep. Sleep is going to acquire p table dot lock. So now you have two locks, and whenever you hold, if there's any point you can hold two locks, you have to worry about the order. Otherwise, there can be a deadlock, right? So this is a real example of why locking kills modularity. You have to worry about these things. Okay. So the convention in the operating system is that p table lock will always be the lowest lock that will ever be taken. So the p table has the least priority in some sense, right? So it will always be the last lock that's ever taken. So if you make that assumption, then this code is correct, right? But that assumption has to be obeyed by all other parts of the code, that you will never acquire another lock after you hold the p table lock. So p table lock will always be the innermost lock, in other words, right? So you have to have this global invariant across your code basically. All right. Okay. Let's look at, so this is I've sketched the implementation, but let's look at the real implementation on sheet 25. So this is sleep on channel and spin lock, right? That's the, and once again there are these debugging aids that the current process should not be 0. Proc is a global variable which is indicating what's the current process that's running on the CPU. It's a per CPU variable. If LK is equal to 0, so lock shouldn't be equal to null. I shouldn't be sleeping without a lock, so lock shouldn't be equal to null. These are just debugging aids, you can ignore it. Here is a check. If lock is not equal to p table lock, acquire p table lock and release the real lock, the lock that was used to call it. Okay, what's happening? So what did I have? I had something different. I said if lock is not equal to p table lock, acquire p table lock, else don't acquire p table lock. You already have p table lock. Here he is saying if lock is not equal to p table lock, acquire p table lock. That's the same, but he is also releasing the lock here. In my code I said I was releasing the lock here. Does it matter if I release the lock here as opposed to releasing the lock here? So I was releasing the lock here. He is releasing the lock here. Doesn't matter? Doesn't matter because you already held p table lock. So now you have created mutual exclusion between between the data. So the data that you're going to access is mutually exclusive because so this area is mutually exclusive because of p table lock, right? Because all you're doing is accessing the proc structure, and assuming that you hold the invariant that whenever you touch the proc structure you'll hold the p table lock, this area is anyways protected from race conditions. So you don't really need to hold the lock for all that long. You could have held it, but it's also okay to just release it a priori, right? Yes. So let's say I have released the lock here, and I'm somewhere here. Let's say another thread calls wake up at this point. What will happen? Another thread calls wake up. So wake up will try to acquire the p table lock and will not get it, right? It will wait for this whole thing to complete, the scheduler to get called. The scheduler recall is going to cause the p table lock to get released. Whoever gets to run next is going to release the p table lock. Recall that the scheduler's invariant was that whoever calls the scheduler should have held the p table lock and then call the scheduler, and the scheduler is going to schedule somebody and that somebody is going to release the lock for you. So this was sort of a very different kind of a structure where one thread acquires the lock and another thread releases the lock, right. So this was a different pattern, and so that's fine. The repeatable lock will be released at this point, and but you have ensured mutual exclusion with respect to the wake up function. So if we had another acquisition of a lock here, then it would be much more prudent to release the lock as soon as possible, so that you don't have more ordering dependencies, right. Because if you have another acquire here, then you would have had to have an ordering dependency between the LK that you have as an argument and this particular lock also, but yeah, but you don't have any acquisition here, that's true. All right. Okay, and let's look at the wake up function. Well, here's the wake up function. The first thing it does is acquire p table lock, calls this helper function called wake up 1 and releases a p table lock, right. And what is wake up 1 doing? Let's see, wake up 1 is just above it. Wake up 1 is just iterating over the p table and checking if state is equal to sleeping and channel is equal to chan, then state is equal to running, right. So this whole logic is being called with p table lock held, all right. Okay. So we understand how sleep and wake up can be implemented under the covers and recall that in doing this we have made sure that the sleep is not just going to sleep, putting the process to sleep in sleeping state, but also releasing the lock, and it's doing it in an atomic fashion, in the sense that no other process can see the state of a process within this whole thing, and the construct that's providing you this atomicity is what? P table lock, right. So p table lock is ensuring that there's atomicity in going to sleep and releasing the lock, okay. All right. All right, so let's look at how sleep and wake up are used inside the x86 kernel, all right. So we have seen before this the system calls called exit and wait, right. In our discussion on Unix system calls, and also in your lab you may have come across exit and wait. What are the semantics of exit and wait? Let's just revise that. So let's say this is a process that calls exit, and here's a parent process. So parent child. So if a parent calls wait, then the wait will never return till one of its children exits, right. So the semantics of wait is that it's going to wait till one of the children have exited. So the dependency is that you will come out of it only after this has called exit, right. So how will an OS implement, let's say, something of this sort? So what are the semantics? That I have to put myself to sleeping state till one of my children exits, and so he'll put me in the runnable state, right. One way to do this is using condition variables or using sleep wake up. So the idea is wait internally will call sleep, it will check a condition. The condition is do I have any children, and if so are they running, and if so I'll start sleeping on some channel, and then exit should call wake up on that particular channel, right. So that if there was a parent sleeping on that channel, then he will wake up and then he can actually come out of the wait.
So why are we using this semantics rather than sigchild one, the signals? Why aren't we using signals to wake up the parent rather than we are using conditional variables?
No, so the signals is just an abstraction at the process level, right. In either case I'm talking about inside the kernel, I'm not talking about at the user level. So inside the kernel, let's say one process has called wait, right. So exit wait is completely independent of the sig child, right. Sig child was there if the parent hasn't called wait, and yet you want to basically inform the parent that I have, my child has, your child has basically exited.
Semantics, same type of thing over here, same process.
So I mean, Unix has both exit wait and sig child, signal mechanism. So I'm right now talking about exit wait, right. So how is exit wait implemented? even signals will require some kind of synchronization. It may not require sleep and wake up necessarily, but it will require some kind of synchronization which will be very similar basically. But this is a simpler thing to worry about. Signals is more complicated to implement, right? And actually XV6 doesn't support signals at all. In any case, even Unix or Linux or whatever will have exit wait without any sick child or anything, right? So if a parent is waiting, then and a process exits, then it's going to wake up the parent so that it comes out of the wait. Okay. So and I'm saying that the waiting can be implemented using sleep, and telling the parent that I have exited can be implemented using wake up. I can use what's the mutex I should use here inside my sleep and wake up if I want to do it. One good mutex to use is ptable.lock, right? After all, I am putting myself to sleep, which basically I could potentially use ptable.lock, and so let's say that's easy. I can use ptable.lock. I need any mutex that's going to ensure that anything that's going to give me mutual exclusion with respect to accesses to my proc structure. So one lock that gives you mutual exclusion with respect to accesses to your proc structure is basically ptable.lock. So that's easy.
So but that will not ensure that only your child can wake you up. Anybody else, any process can wake you up.
No, that's just the mutex. That's just for the mutex, right? Now the question is, what's the channel? What's the channel I should use? Process ID of parent. Great. I can say parents process ID, let's say. Does that make sense? Why does this channel make sense? Let's say I have 10 children, all of them are going to call wake up on one process ID of parent, right? So that's the channel that I'm sleeping on, right? And so it actually makes sense because PID of parent is basically so assuming that your convention is that you're going to use PID of parent only for this exit wait business, then another person's child cannot wake you, right? So a process cannot be wakened by another process's child. You will only be woken up by your own children, right, if you use this convention. What if you used some, instead of using PID of parent, let's say I just used one constant number 1. So I'm always going to sleep on identifier on this constant called 1, let's say.
And any process which exits will wake.
So any process that exits is going to call wake up on all the processes that are waiting. Is that a correctness problem?
Yes.
That may not be a correctness problem because you recall that usually you would, when you come out of sleep, you check the condition again. And so what will happen is if you are sleeping on some global channel that's shared across all the processes, then you will wake up all these other processes, but all these processes, if you have written your code correctly, are again going to check the condition, and everybody except your own parent is going to find the condition to be false. And so all of them are going to go back to sleep, your parent is going to come out. It's wasteful, it's not incorrect, right? So choosing the channel identifier is just a matter of figuring out what are my communication patterns, and then figuring out the channel the identifier that's common to these to the pattern. So in this case it's a parent ID. But if you use something which was more coarse grained, right, like I took the extreme example of a global identifier called 1, assuming you have enclosed your sleep loop with a while condition and a check, that's still correct, but it's wasteful. Okay. All right, good. So let's look at the exit and wait implementations, the real ones, on sheet 23 and 24. So that's your exit function. This function will be called if a process makes the exit system call, and well, it just says here's some debugging aid. The first process, the init proc, should not get ever exit. So that's just a debugging aid. Close all the open files. Right? We have seen this. Every process has a file table, and so XV6 also implements these Unix semantics. And so if a process is exiting, just close all the files. Okay? So that's fine. That's easy. Also, this is some. So the process that was open, that was currently running, its current working directory, that CWD, is also sort of, in the file system knows that this process is accessing this particular directory. So that file system, so nobody can actually delete that directory from under its feet. So for that reason, you know, there's a way to lock that directory, and we're going to discuss this when we discuss file system. So it's basically unlocking that directory, saying that I'm going to exit, so I can unlock that directory. If some other process wants to delete that directory, he's free to do that. Okay. And I set my CWD to 0, current working directory, and now is my logic to implement exit, to do exit wait synchronization. So I do acquire ptable.lock, and I wake up on proc.parent. So instead of the PID of the parent, I'm using the pointer of the PC. So here I'm actually using the PID itself. So proc.parent actually the PID of actually it's a pointer to the proc structure of the parent, right? So instead of using the PID, just use the pointer into the proc structure. That's equally good, right? There's a one-to-one correspondence between PID and the proc structure. So proc.parent, you just wake it up. Right? Notice that I'm not calling wake up, I'm calling wake up 1 because I already have the ptable lock. Right? So here's another example why locks kill modularity. I have to worry about which function will acquire the lock and which will not acquire the lock, and what locks I already have. You know, so it's not nice. Okay, so I'll just wake up the proc.parent and just fall through, and if I have any children, then then I just iterate over the proc table. Notice that I have the ptable lock, so I can safely assume that these accesses are atomic. So ptable.proc so look at all the processes. If I am the parent of that process, right, which means that this process is my child, then do what? I'm going to exit. So basically, so the orphaned process has to be connected to the init process. Recall that this is something, this sort of semantics that we discussed, that if the parent exits, then all its children are connected to the init proc, and init proc is going to call wait so that there are no zombies remaining. Right? And if p.state is equal to zombie, then wake up init proc. What's happening here? So init proc is probably already in the wait loop, right? So init proc is just constantly calling wait, just to collect all these sort of zombie processes. And now now I was a process and I had a child process. I forgot to call wait on the child process. So that child process is just languishing as a zombie there, right? Now I'm exiting. So what I can do is all my zombie processes, if I see any zombie process, I can tell the init proc to wake up because I have attached a zombie process to him. So now his wait is going to return. So that's what I'm doing. So I'm waking up the init proc so that his wait returns if he is inside the wait. Right? This is to wait to ensure that your parent returns. So a process that's exiting, you're making sure that your parent returns from a wait. This is to make sure that init proc returns from the wait, if it is inside wait, because you just attach a zombie process to the init proc. That's right. And then you make your state as zombie, right? Notice that I have not cleaned up my virtual memory. I have not cleaned up my k stack. I have not deallocated my virtual memory. My page table still remains. All the data that I have not freed it, right? I have just marked my state as zombie and called the scheduler. What's going to happen is that my parent process, when it's going to run, is going to call wait, and that's going to deallocate my page table and my k stack. Okay. Why can't I just deallocate my page table here? Because I'm standing on that page table, right? That's the page table that's currently loaded. This exit function is being called in the context of the process that's currently running. And so I can't just deallocate the page table because that page table is actually the one that's loaded into the hardware right now. Now you only change your state to zombie, and now when the other process gets loaded, now you are off the CPU and now you can be deallocated. Similarly, k stack cannot be deallocated because this entire function is executing off that k stack. You can't just deallocate the k stack. It's a parent who will deallocate the k stack when it returns.
So but we can deallocate the user page table as in
you can deallocate the user side of the page table. That's an optimization, and a real operating system will perhaps do that. But x86 just makes it simpler and says the parent will deallocate everything. Okay,
So in case of PrinTOS, the scheduler function was deallocating the K stack. So is that also a possible optimization? As in the K stack, once you reach the scheduler function, and you have seen that the process from which you have just come into that has now exited. So what it does is it deallocates.
Right. So the question is, instead of waiting for the parent to deallocate the stack, is it possible to just on every context switch check if my previous process has become zombie? And if on the context switch, as soon as you context switch, if you have figured out that the previous process that just got context switched out has become zombie, then you can just deallocate its structures. But only some of its structures. You still have to maintain its proc structure because the parent may call wait. You have to, for example, store the exit status, return value, exit code. Right. So those are all possibilities, but that there's a trade-off in doing that. On every context switch, you're going to check whether the previous process context switch process has become zombie or not. Right? That itself has a cost, some cost to it. So whether it's a worthwhile thing to do or not is something that's basically a design decision. Okay, let's look at wait. So here's wait. I just go through my. So firstly, I acquire the p table lock. Once again, what's wait going to do? It's going to go through the entire p table and it's going to check if I am the parent of this particular process and if it is zombie. Then I can just return. Right? I called wait on something that has already exited, so I can just return, right, because it is already zombie. So I can just return from there. So I just sort of go through the p table. If I am not the parent of that proc, of that p, then continue. Otherwise, I am the parent. I just check if it is a zombie. I found a zombie. My wait doesn't need to sleep. My wait can just return. So I found one. I can just free all its things. So I can free its K stack. I can free its page directory. I can set its state to unused, right? And I'm doing this under the protection of p table lock recall. And then I just release the p table lock and I return the process ID of the process that I just released, right? That's the one that was zombie. So I return the PID.
So do we need to actually set these fields to 0, because anyways once you have mounted unused, we are not going to access these.
Sure. I mean, do you need to set it to 0 because you have set it to unused? Yeah, I mean those small things can be done, right? I'm not sure what other parts of the code are relying on what invariants they maintain, but you could do that. Sure. All right. Now, if I don't have kids, right, which means I don't have any children, and I called wait, I don't need to wait for anything, right, because I don't have any children. So I'm calling wait. So I just return with a -1 status. That's all, right? And then there is this field called proc.killed. I'm going to discuss this next time. Let's wait on that. But at this point, I know that I have some children. This process has some children, and it has some children that are not yet zombie. So what do I have to do? I have to wait for them to become zombie. So I just sleep on proc, and this is the ptable.log that's protecting that. Right? So that's basically exit wait. So now this process will go into a sleeping state. As soon as somebody exits, he is going to call wake up, and the channel is going to be his parent. I slept on my own ID, right? He is going to wake up on his parent's ID. So that's how the synchronization is happening. Okay, let's stop here, and I'm going to discuss the kill system call and how the kill system call is implemented using these mechanisms, and how the IDE device driver, how a disk device driver uses synchronization, and how a device driver works internally to do this thing. And also we're going to discuss virtual memory, and we're going to start the topic of virtual memory and paging in the next lecture.